The first problem set is will be on, the problem sets will be due on Thursdays. And so the first one is coming this week, and then we'll be due in 2 weeks. I've heard from some of you about your schedules, not everybody. So if we want, we'll just pick a time. Otherwise, if you don't send me something, I'll talk to our TAs. All right. So where were we? So what we're talking about is continuous variable quantum optics. Okay. And as we've discussed many times, when we think about the quantum field, we can think about different degrees of freedom, either the particle or kind of the wave degrees of freedom associated with the quantum field. And in kind of modern parlance, people talk about discrete variable and continuous variable quantum optics. And that's really just to say what kind of observables or properties of the field are we talking about? Are we talking about the particles or aspects of the wave? The waves here, in particular, what the variables we think about are the quadratures, x and p, which represent the quadratures of the amplitudes of oscillation, okay? And the form, when we think about that, is we're thinking about a phase space as the description of the oscillator, as borrowing from the classical description of the classical simple harmonic oscillator. And when we're dealing with the quantum description thereof, there is an algebra that we use and that we have to remind ourselves of and familiarize ourselves about. And so the phase space algebra, sometimes we call the bosonic algebra. We're reminding ourselves about some of that. The operator that rotates a state in phase space by an angle theta in the clockwise direction is this operator, and these are the unitary transformations on that acts on the complex amplitude, the annihilation operator, and the quadratures, reminding ourselves that this is a passive rotation, which is why it goes the other direction. And the displacement operator is a very important operator, the algebra thereof, that displaces me in phase space, okay? So these are things we've studied in the past, we need to remind ourselves about. And as of course we know, a coherent state is the displacement operator acting on the vacuum state. And the coherent state has vacuum fluctuations around the mean value. So as we know, the fluctuations in x and p along any quadrature are equal. And are equal to 1 over root 2, such that this is a minimum uncertainty product. Okay, and this is true for all theta. Okay. Moreover, what we discussed last time is that for what we sometimes call classical light, which is to say light arising from a classical current. So if the current is some C number current, and such light we know for a given mode would be a statistical mixture of coherent states, that in that case, the fluctuations in the quadrature amplitudes are always greater than or equal to 1 over root 2, which is the vacuum noise. The minimum it could possibly be is 1 over root 2 set by vacuum noise, okay? And if we have a state that violates this, that state could not have arisen from a classical current, okay? And an example of a state that violates that is for a squeeze state. This is less than 1 over root 2 for some theta. Okay? And a pure squeeze state is one which such that it's a minimal uncertainty state but this is true. Okay, so the product is the minimum, but for some theta, some phase quadrature, it's less than the vacuum noise. Okay, so a squeeze state we often draw in phase space as something which has a reduced. So if this is the vacuum fluctuations of a coherent state, the squeeze state will have less fluctuations, for example, in the X quadrature. So we might have something that looks like that, as we discussed last time, where this fluctuation here is less than 1 over root 2. So this might be equal to this fluctuation in X, for example, is some parameter which we'll call e to the minus r 1 over root 2, and the fluctuations in P must thus be increased by the inverse of that, plus r. Okay, so this is an example of a squeeze state. It doesn't have to be squeezed along X. This is just one example of a squeeze state. And so let's just think about what does this mean operationally to say we have these kinds of fluctuations, okay? So let's think about, let's say we have the free evolution. We have some state that's prepared in some initial state, and we ask what is the free evolution, okay? Okay. Suppose at time t equals 0, the state is a vacuum. What is the state at a later time? If it's a free evolution. If the vacuum is an eigenstate, so it's always the state of vacuum. Okay? What if the state, free evolution is according to that unitary evolution. And that, of course, is a rotation by that angle in the notation we used earlier, the rotation operator somewhere. There, okay? What if the state were initially a coherent state? What is the state at a later time? Ooh, well, that's actually not correct. Yeah.
The coherent state with it rotating now.
That's right. So it stays a coherent state, but it has a new amplitude. Okay? So if I were to look at the in this case, if I ask what is the mean x and the mean p as a function of time, well, for the vacuum, it's always 0, right? And the fluctuations in this at any time are always the same. They're the vacuum fluctuations, or 1/√2 for the RMS, right? For the coherent state, the mean x as a function of time is what? Well, it's just the rotated, right? It's the mean x at 0 cos omega t plus the mean p at time t equals 0 sine omega t, and similarly for p. Right? And the fluctuations for the coherent state are also at all times the same. So what that would say, if I were to do a measurement of, and I will come to this later in the lecture of how we would do such a measurement, if I were able to measure the quadrature x or p as a function of time, what am I going to see? Well, so now I'm looking at x, the value that I see, and measure the value of x as a function of time. Well, firstly, these are not eigenstates of x or p, so I'm going to get a random outcome. On average, for the case of the vacuum, I get 0. Right? So for the vacuum, on average, I get 0. But in any run of the experiment, I'm going to get some random outcome. Okay? According to a probability distribution, which is the probability of seeing x given 0, which of course is a Gaussian in this case. So what I'm going to see is something that looks like this. Well, it's going to be single value. I'll see some noise. And, there's some RMS. If I were to run this shot to shot, I'll see a different value each time I run. If I re-prepare the vacuum state, I'll see a different run of the experiment. We'll see a different noisy signal, but there's some spread in this, which is the vacuum fluctuations. Okay. Similarly, for the case of the coherent state, what would I see? Well, again, the coherent state is not an eigenstate of x, but we know what the mean x is and p as a function of t. And this will have some this is the mean x as a function of time, right? Is this thing, depending on what it is at individual time. But in any run of the experiment, I'm not going to see this mean value. I'm going to see something that has some variance above that. So I'll see some noisy with the same noise variance as etc. So there's some, when we draw that bubble, that what we're really drawing is the 1 sigma variance away from the mean, right? So this is my delta x, which is again, 1/√2. Okay, so there's noise that I see in X, which we might call quantum noise, or shot noise, as we'll remind ourselves of what that term means, which is related to the fact that the state of the system is not an eigenstate of the particular observable that we're looking at. And so in any run, we're going to get some random outcome, not determined. What about the squeeze states? What would we expect to see for the squeeze states? Well, we can think about different kinds of squeeze states. So one kind of squeeze state is called squeezed vacuum. In a squeezed vacuum state, the state has a mean of 0, okay? So on average, the quadrature, any quadrature has mean 0, but there are fluctuations about them, okay? So, if I were now, for this case, if I were to look at what the x is as a function of time, what is the mean x, what does the mean x do as a function of time if the state is initially this state? What is the mean x as a function of time in this case? It's 0. Firstly, what happens to this state as a function of time? Well, it rotates around the origin at angular frequency omega, right? So, you know, what this thing does is it rotates like this, such that at a quarter of a period, it looks like that. A half a period, it comes back to itself. So at a time where omega t is equal to pi, so let's write this as a function of omega t, because that's the right units to think about. When omega t is pi over 2, it looks like that. And then omega t equals pi, it comes back to itself. So the state comes back to itself with a period of pi. The mean is always 0. Okay, so the mean would look like this. But if I were to draw the envelope of the fluctuations, let's say this is equal to what we would see, this is the envelope that we would see for the vacuum. Okay, so let's say that this is 1 over root 2. But this guy has, the squeeze state has reduced fluctuations relative to the vacuum. So if I were to measure this, I would generally see something which is less noisy here, right? And what I'll see in this situation is something that looks more like the following. Let me see where to make so. So this is the envelope of the RMS fluctuations that I would see in the squeeze state, which is to say, here I would see a little less noise. Then the noise would get really bad, and then the noise would get really low, and then the noise would get really bad, and then the noise would get really quiet. And I'll see this kind of, depending, I mean, it's not periodic. This is meant to be noise, and it's going to be some random Gaussian value somewhere in between these things. It doesn't cut off exactly, go above or below. This is meant to just be the picture of what the RMS deviation from the mean is and how it depends on time, okay? So we'll see this kind of beating, which is to say that if I somehow can lock my system to be looking at the squeeze state at this phase, I'll have noise that is reduced below the shot noise limit. Whereas if I had it locked at this phase, I would see noise that is much bigger than the shot noise limit typically, okay? That's an example of squeezed vacuum. I could think about a squeezed amplitude state. What does that mean? What that means is that now I have some mean field that's not zero, but I want to say that the amplitude is well defined, more well defined than is possible if I just had a coherent state. And so in that case, I would have a state that was squeezed like that. Well, it should be like that. Okay? So in this case, my vacuum noise would have been this if it were a coherent state, but I've squeezed along the quadrature that is perpendicular to the phase direction. So what would this look like compared to what we had for the coherent state? Well, in that case, again, I could say, all right, the mean does the same thing as the coherent state, right? The mean in this case is going to do what we had for the coherent state, which is, just a cosinusoidal oscillation. If we had a coherent state, the fluctuations are the same no matter where I am in the phase of the oscillation. Whereas here, when x is 0, I have huge fluctuations. I'm sorry. When x is 0, I have the minimum fluctuations. I'm sorry. Get this backwards again. The phase. So what this thing is, the phase is very uncertain. Where this thing passes through 0 is completely uncertain. Is not completely, but is much more uncertain. But its amplitude is well defined. Okay. So what that means is I have an envelope that looks like this. Here it's very little. Here it's very big. Here it's very little. So let me get my drawing because I'm not going to be able to visualize this well without my cheat note.
So the noise is minimum whenever the average x is 0, right?
Correct. When the phasor is here, this thing has the maximum uncertainty in x.
Yes.
Okay. But when it's at its maximum value, it has the minimum uncertainty. So when x is at its maximum value, which is where it reaches its peak, I have the minimum uncertainty. So I can tell what its amplitude is, but I have less information on its phase, which is where it crosses the arc. And there's this kind of trade-off, as we know, between amplitude and phase. Let me try to draw this picture a little bit better, maybe. Right. Good. Let me. So the idea here is we'll have much less noise near the peak and much more noise where it crosses the origin. this is an amplitude squeeze state. In contrast, I can think about a phase squeeze state. They're all squeeze states, it's just how the orientation of the squeezing is relative to the mean. So now I want to say I have a state whose quadrature is squeezed along the phase direction. So how would that look as a function of time? Again, the mean x does exactly the same thing as we said before. It's some cosinusoidal thing. But now the minimum uncertainty is where it crosses, okay? When x is 0, I have the minimum uncertainty. When x is at its maximum, I have the maximum uncertainty. And so this kind of thing would look like this. Yeah, I would have this kind of envelope. It has so that I have less uncertainty around here and much bigger uncertainty near the amplitude. Again, this from shot to shot, I'll see a different trace if I have to measure this. These dotted lines are just meant to emphasize what is the variance, what's the 1 sigma RMS away from the mean. You can thus imagine what a squeeze state might be used for if I want to improve the precision with which I could either know the amplitude or phase of an oscillator. And that certainly would be something I might be interested in some metrological application, which is one of the places they were invented for. All right, so with that said, how do we describe these things mathematically? So the star of the show is what's called the squeezing operator. It's another piece of the boson algebra that we need to familiarize ourselves with. The squeezing operator is defined, I define as follows. It's a function of a real parameter to start, r, and it's e to the half r alpha a squared minus r a dagger squared, where r is real. Okay? Let's just say that it's positive. It doesn't have to be, but let's define it to be a positive number. Okay? So, as we discussed last time, this is a unitary operator, right? Because the thing in the exponent is anti-Hermitian, and thus it's a unitary operator. Call it e to the minus a, where a is an anti-Hermitian operator, where a, in this case, is a half r a dagger squared minus r a squared. Why did I put the stupid minus sign in there? Well, because I'm interested in thinking about our algebraic relations similar to the, what's the unitary transformation that, so I will define the squeezing operator acting on that as squeeze vacuum. It's an example of a squeeze vacuum state. Okay. we want to understand this property, so we want to see what the unitary transformations are. So the first question I have for you is, how would we find that unitary transformation? Well, we use Baker-Campbell-Hausdorff, okay? So S dagger here, since this is anti-Hermitian, is e to the A, e to the minus A. Okay? That's why I put the minus sign in there, because I didn't want to carry on with their minus sign. Because I remember this formula. Maybe you do too. That formula is that this is equal to A plus the commutator of A with A plus a half the commutator of A with A with A plus dot 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 1 over n factorial, the multiple commutator of A with A n times. Okay? So what we need to do in order to determine this transformation is to calculate these commutators. Okay, so what is this commutation relation? Well, that's equal to a half R A dagger squared with A, which is equal to minus a half R A dagger. I don't know a half. I got rid of the half because I do it twice. Okay? And thus, the commutator twice with this is equal to R squared over 2 the commutator of A squared with A dagger, which is equal to R squared A. So, when we put all that together, what we see is that we keep, because the fact that this comes back to something that's either linear in A or A dagger, the repeated commutators just go back and forth between A and A dagger, and we get that this is equal to the sum over n even R to the n over n factorial times A, and then every one of these guys has a minus sign, and so I have minus sum over n odd R to the n over n factorial A dagger. All right? And so we have to scratch our heads and to remind ourselves of what this Taylor series is. Anyone have any thoughts? If it was all n, it would be exponentials, right? But it only has the odds or evens.
Cosine and sine.
They're not cosines or sines because those are the alternating signs. So they're close. But you're close. They're coshs and sinh,
Oh, yeah.
right? So this is the hyperbolic cosine, and this is the hyperbolic sine, which we remember is e to the r plus e to the minus r over 2, and this is e to the r minus e to the minus r. Okay. And just because it's worth remembering, cosh squared minus sinh squared is 1. The cos and sines add to 1. Okay? Oh God. Yes, we have to remember that. All right, so what we have then is that S dagger A S is equal to cosh R A minus sinh R A dagger. And if I take the dagger of everything, I get that. Okay? And thus, By the way, this is known as a Bogoliubov transformation. Bogoliubov transformation. Bogoliubov wrote this down originally in the context of thinking about the quasi-particles in superfluid helium, because we'll sort of see a relationship here. Anything where you have interactions, the lowest order effect is squeezing or Bogoliubov. That's something we'll understand a little bit more in a little while. So the Bogoliubov transformation sort of is kind of like a Lorentz transformation about that you have in space and time, but between A and A dagger. There's an intimate relationship to that group, the Lorentz group, and this group. That's an aside. What about the action of the transformation on the quadratures? How would you calculate that? Well, we could just write x in terms of the sum of A and A dagger. So this is S A plus A dagger over root 2 S, which, because I'm lazy, I will call scripty C Cauchy and scripty S Sinh. And so this is equal to Cosh A minus Sinh A dagger plus Cosh A dagger minus Sinh A over root 2, right? Which is equal to Cosh minus Sinh over root 2 A, and then I have plus Cosh minus Sinh A dagger, right? And what's Cosh minus Sinh? E to the minus R, right? This minus that is e to the minus R. So this is equal to e to the minus R x. And similarly, we can find that the unitary transformation on P is e to the plus R on P. It has to preserve the commutation relations. The commutator of the unitarily transformed x with the unitarily transformed P is the same as x and P, as it must be, okay? All right, so with that, we can calculate the properties of the squeeze state as we intuited just thinking about phase space. So if I ask, what is the mean x of a squeezed vacuum, that is equal to the squeezed vacuum state we said was the unitarily evolved vacuum according to the squeezing operator, which is this C number times that, which is 0. Okay? And similarly, if I ask what is the mean momentum quadrature, P quadrature associated with that, it's the same biz. But now what about the fluctuations? So if I ask what's the variance in the fluctuations, that's equal to the mean of x squared minus the mean of x squared, but the mean of x is 0, so I just have to calculate that. How am I going to do that? Well, I do the same thing. But the important trick of the trade is that this is a unitary operator, and so it can come inside the exponent. That's a little mathematical trick. That you can convince yourself of. Why is that true if you haven't thought about it?
Insert an
You just insert, I write x times x, and then insert an s dagger s in there. It doesn't matter what the power is. The unitary transformed on x to the n is the unitary transformed x to the power n. Okay? This is this squared, which is equal to e to the minus 2r mean of x squared to the vacuum, and that is equal to a half. Okay? So the fluctuations for this particular state, for the squeezed vacuum as I've written it, are e to the minus r over root 2. As I drew, this is just a particular case. And similarly, the momentum fluctuations are e to the plus r. Okay. How many photons are there in a squeezed vacuum state? You might say 0, right? It's the vacuum, right? The vacuum doesn't have any photons, but that's, an unfortunate use of the word. Because if it was 0, then the mean number is 0, then it would be the vacuum, and it's not the vacuum. It's something different from the vacuum. How would we calculate it? Well, that looks like the mean number of photons in this field. Which is equal to what? How would we calculate that? We could do the same trick. We could do the unitary transformation like that. And then we shove in an S dagger. Right? And then we have to write this is equal to cosh A dagger minus sinh A times cosh A minus sinh A dagger. I did the Bogoliubov transformation on A dagger and on A. So, of the 4 terms, when we multiply them out, which is the only one that survives? Remember, if A acts on the vacuum, it annihilates it. If A dagger acts on the bra version, it annihilates it. So the only term that survives is this one, which is the vacuum. Right? Which is 1. Because you commute that through, and we get 1. So this is the mean number of photons in this thing. It doesn't have this, so squeezed vacuum ain't vacuum.
And it tells us we have to put energy.
Yep.
Which is squeeze.
We do.
So it's one extreme limit of the speed state, just the eigenstate of the x operator, whatever it is.
Yeah, in this case, if it went all the way, is the squeezing parameter into it, it would become an x eigenstate, indeed. Okay? Now, how do we understand, or what at least one way to understand the fact that how is it possible that the fluctuations in, say, X for this particular squeeze state are below the vacuum noise? When we said that any state which has a certain number of photons must have fluctuations that are in X that are at least equal to that of the vacuum. For the other states with more photons, they have bigger fluctuations in X, right? The fluctuation in quadrature, X as a function of n is n plus 1 over 2, right? The more photons you have, the more fluctuations you have in the quadrature. And this thing only has more photons than the vacuum. So how is it possible that the fluctuations in X are less than what we would see for any number of photons? Well, I mean, at the end of the day, I'm only measuring X. I'm not measuring P.
So your original expression where you prove the inequality is that you have the buried in that vacuum 1/2 plus an expectation value or a variance that was due to the Glauber-Sudarshan
Right.
function. That's assuming that's a proper probability distribution.
Right.
It's going to be strictly positive.
Right.
So if it has a negative component, then you can't do Cauchy-Schwarz.
That's right. So it's certainly going to violate, you're absolutely right, Cole. I mean, our proof that the fluctuations must be bigger than 1/2 came from the assumption that the Glauber P representation was an honest-to-God probability distribution. So clearly this state doesn't have that, and so it's going to violate that. But I still want to have a different intuition of what's going on. If we have a state which, so let's look at the squeeze vacuum state. Let's suppose we had weak squeezing. So let's just look at the expression for our squeezed vacuum. For this particular guy. Which is approximately equal to 1 plus 1/2 A squared minus A dagger squared acting on the vacuum for R small, okay? Which is to say that the squeezed vacuum state is a coherent superposition of the vacuum and states with more photons. In this case, it has a superposition of no photons and 2 photons, okay? But importantly, it's not just 0 or 2, a statistical mixture of 0 or 2, because if it were a statistical mixture of 0 or 2, then the fluctuations would just be the statistical mixture of those two, which is always going to be more than the minimum. So it's an interference effect. The squeezing is intimately related to the interference between the two possibilities. The coherent superposition is important. So if we were to look at, say, what is the mean of x squared for this thing, okay? So that this is going to be, let's take everything only up to lowest order in R small, so let's keep terms only to linear order in R. We neglected quadratic terms here. So what am I gonna get? I'm gonna get the vacuum noise, right? Then I'm gonna get minus R over root 2, 0 x squared 2 plus 2 x squared 0. Okay. Now we can do a little, we can calculate those things again, thinking about, you know, creation annihilation operators, right? And so x squared here is going to have an a squared plus a dagger squared, and then terms like a dagger a plus a dagger. Over 2. And in this case, only this guy survives, where I annihilate 2 photons, which would give me a root 2. And so what I'm going to get in this case is 1 minus 2r over 2. That minus 2r is coming from this, which is, you know, approximately a half times e to the minus 2r for r much, much less than 1. I mean, I may have screwed up the algebra, but this is the basic point. You know, I have a root 2 and 2, I'm not going to do it. But the main point I want to emphasize here, it is the interference, the beating between these two amplitudes that enables us to beat the classical noise limits. The coherence is important. Okay. Good. All right. Questions? All right, let's see, where are we in this? Oh yeah. Good. So another piece of intuition I want to share relative to this story is how we can think about the squeeze state from the point of view of wave mechanics, okay? If I wanted to, I can think about the representations of states in terms of the quadratures. We would call these things the wave functions. But again, I want to emphasize, this is not the wave function of the position of the photon. This is the probability amplitude of measuring the quadrature x or the quadrature p, which we will talk about. I keep saying, I'm promising how we actually do that very soon. Promise, next thing. Okay?
Hold on to something.
Yes. So, I ask you now, what is this object? If I have n photons in the field, and I want to know what is the probability amplitude of measuring the quadrature value x. This is the wave function in wave mechanics associated with the eigenstate of the harmonic oscillator with energy eigenvalue n plus a half times omega. What is that wave function for a harmonic oscillator? It's a polynomial times a Gaussian, right? So it's some constant, some normalization constant, e to the minus x squared over 2 times a Hermite polynomial with some normalization. I don't know if there's a root 2 in there from, I can't remember, I should know, minus, oh yeah, there's nothing, that's lovely, I love that so much. Where is a Hermite polynomial? For the vacuum state, the fluctuations are Gaussian. Okay, so if as we remember, if we look at the wave functions thought about as particles in a well, that is a harmonic well associated with the harmonic oscillator, we have, you know, the energy levels of the harmonic oscillator equally spaced, where the ground state is a Gaussian, the first excited state is a Hermite polynomial that looks like this, the second one looks like that, etc., etc. Something like that, right? Now, what about the squeeze state? So this is the vacuum, which has, as a function of x, this is the wave function, which is the probability amplitude of measuring x, which is going to have this Gaussian spread with a RMS of 1/√2, right? Which is, say, I would sample each time I would measure, and that was, you know, my horrible drivers of noise was meant to draw this sampling from this probability distribution. What about the squeeze vacuum? What would it look like as a wave packet relative to the quadrature variable? Well, it has the same, some mean, and it has some fluctuations around that. But in this case, if this were the vacuum state, the squeeze state is something, say, at the initial time, that has less fluctuation. It's a Gaussian wave packet, but it has reduced uncertainty, okay? At time equals 0. What happens to it as a function of time?
Fluctuation increases.
It's going to breathe in and out, right? And it's going to breathe to become, at a later time, at a quarter period, have broader fluctuations, and it's going to be a breathing wave packet.
What's the difference between a breathing wave packet and an oscillator?
Well, I'm saying the mean stays at 0, but it's just its uncertainty is going back and forth. Okay, it's only my jargon here, no one else would use that jargon.
It's oscillating in uncertainty.
In its uncertainty, but its mean stays fixed. And what is the frequency of that oscillation? If the harmonic oscillator has a frequency omega.
Omega by 2.
Twice omega.
Twice omega. Sorry.
Right, yes. Right? Because it comes back to itself in half the period, right? We will see in a moment, this is actually, in some sense, a completely classical description. If I were to take an initial set of initial conditions of harmonic oscillator that were distributed in position and momentum with a particular probability distribution, each point will undergo oscillations and it will come back to itself at half a period and then undo. So it's just every half period it returns to that. It's that breathing wave packet. That's the breathing wave packet right there. All right. So now, how do we think about this factor of 2? I just thought about in terms of this, you know, this picture of classical oscillation. You can see how it's going to come back to itself. From the point of view of the superposition that exists quantum mechanically. So this state, this particular squeeze vacuum state, is obtained by operating this operator on the ground state, on the vacuum. Which means that this state is a superposition with some coefficients of n, but n is only even. Now, you would have, it's a good problem one we might have for homework for what that coefficients are. But this only is a superposition of the even parity eigenstates. It has a superposition of the vacuum, 2 photons, 4 photons, 6 photons, etc. And as I was indicating, it's a harbinger of our discussions to come. The squeezing thus is somehow related to pair production of photons. The fact that photons are created in pairs, that's a very different process of the linear displacement where we have an individual uncorrelated sets of photons. This pair production of photons is one of its hallmark non-classical features. But it's in a squeezed vacuum, you don't just have pairs of photons, you have a superposition of maybe you had no photons, and then maybe you had 2, and then some smaller amplitude of maybe 4, which is 2 pairs of 2 photons, etc. Okay? So the physical process is that. Excellent. All right, so now, as promised, how in the world do you actually measure these quadratures? Oh, maybe I would lie. Oh, if you don't mind lying, that's going to be next time. So I have one more thing to do. Liar, liar, pants on fire. What we just talked about is one very specific squeezed state, the squeezed vacuum that was squeezed along the x quadrature, but we want to talk about the more general squeezed states that I attempted to try to draw for you. So firstly, let's talk about a squeezed vacuum state, but there's one that's squeezed along a different quadrature. So this state, I'm going to draw as a squeezed vacuum state, but squeezing is along x theta rather than along x. Okay? So how would I obtain this state? I need to rotate the squeezed vacuum that we rotated anti-clockwise. So this state is squeezed state, oops, rotated of the squeezed vacuum. Okay, rotated counterclockwise. And that is our dagger acting on the squeezing operator, operating on the vacuum. But now I can put in an R dagger R and write this as the rotation transformation on the squeezing. Okay? How am I going to do that? Well, this is another trick of the trade. When you have a unitary transformation acting on the exponential, you can shove the unitary in the exponent. So, that then is equal to e to the minus the r 1/2 r e to the minus 2 theta A minus R e to the plus I 2 theta A dagger squared. Because the unitary transformation on A is e to the minus I phi or theta, and then I have it squared. All right? So this is a more general form of the squeezing operator with a complex squeezing parameter. So I will call this S of zeta, because everyone loves to write zeta, second best thing to C. Zeta I have defined as R e to the I2 theta. Okay? That's the way I'm defining it. And what that means is that the quadrature that I'm squeezed at is defined by half the argument of zeta. Okay? So I'm squeezed along theta here. That is the quadrature that has the minimum squeezing. Right. Very good. So, we need to write down the generalized Bogoliubov transformation. I can do that using this algebra here. The squeezing operator with the complex guy is the rotated version of the one I just defined at the beginning of the class. Looks like that. I know this algebra is kind of boring, but it is what it is. And this is that, right? Because it's going in that direction. And then I got the Cauchys and Cinches. And when all is said and done, what I get is the following. This is equal to cosh R A minus e to the I2 theta cinch. A dagger. And similarly, S dagger on A dagger with the complex squeezing parameter is cosh R A dagger minus e to the minus 2 I theta cinch R A. So, I will leave it as an exercise for the reader. Suppose I ask, I'm going to measure the fluctuations along some arbitrary quadrature phi. Right, this is the mean of x phi squared minus the mean of x squared, where x phi is cosh phi x plus sinh phi t. This, of course, we can easily show to be equal to 0, but with a little bit of work, the answer is this. So let's try to think about what does this mean. This says that the fluctuations in x along the quadrature direction phi are minimum when phi takes on what value? Theta. When phi equals theta, I have fluctuations either minus 2r times the vacuum fluctuations. And when the phase quadrature phi is rotated by 90 degrees relative to theta, then I have the maximum fluctuations. So if I were to plot this as a function of phi, what I would see is the following. Here, say, is the, so I'm looking at the variance in the fluctuations as a function of phi. This is the vacuum level. Okay. There's some particular value at which it dips, and then it goes above, and then it dips, and then it goes above, and then it dips, where this is equal to theta. This is theta plus pi over 2. So the fluctuations that I would, as we expect in the phase quadrature for a squeezed state, are phase dependent. When the phase quadrature measuring is equal to theta, I have the minimum fluctuations for my definition. 90 degrees away from that, I have the maximum fluctuations. All right. So let's maybe just preview. Oh, the last thing I wanted to say before the lecture. So what about those things that I looked at were like the squeezed amplitude of squeeze? I could have something which is, you know, has some arbitrary squeezing relative to the mean field. Okay. This kind of state, which has an alpha and a zeta, is a displaced squeezed vacuum. So instead of displacing the vacuum, I displace the squeezed vacuum, where the squeezed vacuum is squeezed along some quadrature, and the displacement is in whatever direction it is. Note, this is not equal to squeezing and then displacing. Check that for yourself. It's a different physical process. These things don't commute with one another. Okay, so the squeeze state, as we define it, is the displaced squeezed vacuum. So, question: we can quickly just a little algebraic check. What is the mean x in this case? Well, again, I use this algebra over here. Right? And this is equal to what? The displaced x. So this is x plus the square root to the real part of alpha, right? Which is equal to, I know I have ink all over my nose now, don't I? We'll see. Is equal to what? It's equal to plus the square root of 2, the real part of alpha, times right? This is 1. And what is that? 0, right? I mean, we can write x as some combination of a and a daggers, that's going to be 0. So it has the same meaning as for the coherent state, and similarly for P. But the fluctuations in X and P are as for the squeeze vacuum, this function. And similarly for the P value. So these things have the mean of the coherent state, but the fluctuations associated with the squeeze vacuum. All right. So that is the algebra that we have to familiarize ourselves with. Next time we'll talk about how we actually measure these things, at least as in a high level theory kind of way. And then we'll talk about how physically we actually create them.